one thing I forgot to mention about the general slicing method is, of course, that it's general, which means that this method works even if it's not rotational. This method works for non-rotational, i.e. not on a lathe, not on a pottery wheel, not a barrel, non-rotational objects, which is what we're going to practice with right down below. Oop, I lost space for my parentheses right there. All right, so non-rotational objects, this will still work. As a matter of fact, this is the method that will work for non-rotational objects. In other words, non-rotational meaning not as symmetrical, say. They don't have an axis of symmetry, no axis of rotation. That's what that means, right? There's no spinning around anything. Okay, so let's practice one with that. However, there's typos all over this, and I'm sorry. So let me just fix these right now. The problem I've set up is not the problem I have a picture of, and I think we should go with the one I have a picture of. So it's going to be, imagine a solid whose base is the region bounded by the curve y equals 1 minus x squared in quadrant 1. Sorry. And it's bound by the x-axis as well. So it's in quadrant 1. I can just say that. That's enough. Sorry about that. Typo. Sorry. Whose cross sections are squares that are perpendicular to the x-axis, which is what is drawn here. We're going to compute the volume of this shape. So it's sort of like a parabolic cube, kind of. It's like a weird stack of post-it notes. Like every post-it note is stacked up in here, but the post-it cube is kind of shaved off. So like up here, you've got little teeny tiny squares that are post-it notes, and then way back at the bottom, you have bigger squares that are post-it notes. So it's like imagining a post-it note cube, but very weird shaped. And of course, this is not rotational, so we can make a little note. This is not a rotational. There's no axis of symmetry. So I'll just make a note. This is not rotational, so general slicing is the only method we have. Now, grant you that's the only method we know right now, but you're going to learn a few more, and so you want to be able to refer back to these notes when you have other methods and go, oh, that's why we had to do it this way. So we must use the general slicing method. When they are rotational, it's actually a little bit easier in many respects. Okay, so I know I'm going to have to use the general slicing method. So that means that the volume, which is V, will be equal to the integral. Now I need to figure this out first. Am I going to do this with respect to X or respect to Y? But when I look at this thickness right here, and you'll notice, by the way, that's the x-axis, that's the y-axis. The z-axis is actually kind of right here. You can see it in this graph right there. That's the z-axis. That's three-dimensional drawing. You're actually kind of looking at it from the side as opposed to looking at it from up above. So if you looked at it from up above, you actually have a parabola here, right, which is 1 minus x squared. Right? So you have that parabola, that's this parabola shape right here, right? And then, actually, it's from here down. So this spot right here, is this spot right here, right? Because you're out on the x-axis, which is right here. So this is the x-axis. And this is the y-axis. That's the more common way we are used to looking at things. But in Calc 3, you're going to spend a lot of your time looking at things from 3 dimensions, which means you'll need to be able to see the dimension. So you can't see it here because this object's kind of coming up into space, into the air above that graph. And so that's not super helpful for us, but that's what's happening. Okay, so when I think about the side of one of these sides of this triangle right here, right there, or sorry, rectangle, square, geez Louise, it's a square. It says right in the problem it's a square. That's coming right across here. That edge right there is that edge right there, and then there's a square kind of up above this in space. Okay, so I can tell that that square has a thickness, and that thickness is on the x-axis because it's perpendicular, right? So the thickness is dx. Primarily because it says it's perpendicular to the x-axis. So that's what's let you know that it's going to come across that way. So I'm going to leave some space here, but I know that I'm going to have dx here. Then I'm going to need my area of my cross section. I'll figure that out in a minute. And then I need my beginning point and my ending point. Well, it tells us that it wants us in quadrant 1. So that means that I'm going to have to go from 0, right here, x equals 0, right there at the start, over to this point right here, right? So I'm going to look in quadrant 1, so I'm going to go from 0 to something. So I just need to figure out what that something is. So my beginning point is 0, no problem. For my end point, I need to find when that value hits the axis. And I kind of did it with a pink dot earlier, so I guess I'll just stick with that. All right, so there's the end. So this was the start right here, my integration. So I'm going to start stacking my weird post-it note stack at that end. I'm going to end up over here. So over here is the end, right? Or if you're looking at it from up on high, that's the end and that's the start. Sorry, got dyslexic there for a second. All right, so how do I find that endpoint, right? So to find the limits of integration, let's see here. Well, at that point, the curve y, which is 1 minus x squared, is equal to 0 because you're sitting on the x-axis. So that means that 1 is equal to x squared, which means x is equal to plus or minus the square root of 1, which means plus or minus 1. Now that said, I only want positive 1 because we're in quadrant 1. If we were in quadrant 2, then x equals negative 1 would be lovely. But since we're in quadrant 1, that means that I'm going to go to 1 right here. Wonderful. All right, so now all I have to do is figure out my area of my cross section. So the beautiful thing about this is that this cross section right here is a square. All right, so let's make a note of that. So a of x equals the area of a cross section, but that means it's the area of a square. Because it says in the problem that the cross sections are squares. They're weird post-it notes, right? It says right here, squares. That was not a typo. All right, so if it's going to be a square, then I need to know what the side is and then square it. That will be the area of a square. Okay, so what's the side? Well, the side is the distance from the x-axis out to that curve, but that's what that is. That's 1 minus x squared. That's the definition. That's what that always means back in geometry and algebra. So, right, so this is 1 minus x squared, which would be 1 minus 2x squared plus x to the 4th, if you want to know. All right, so I'm going to go take that and put it into my lovely volume integral. So I'm going to go from 0 to 1. And I'm going to integrate 1 minus 2x squared plus x to the 4th with respect to x. Okay, well, that's relatively easy. I'm done with all the colors though. All right, so if I integrate this would be x minus 2 thirds x cubed, because of course we add 1 to the power and then divide, plus 1/5 x to the 5th, add 1 to the power, then multiply by the reciprocal, which is what division is. And then we're going to take this from 0 to 1. Well, with most polynomials, with polynomials with integration, the 0 is not going to matter because 0, 0, 0 makes 0. So all I need is putting 1 in. That's 1 minus 2 thirds plus 1/5 minus 0. Right? And that value, let's see here, love Desmos, is 8/15. And if I want to check myself that I foiled correctly or that I found the integral correctly, those values are all equal to each other. So I love that. And there we have it. Oh, volume. So if I gave units, which I did not, let's assume the values are in, I'll just put it right up here. Assume x and y are in centimeters. This is terrible typo up here. All right, so x, y in centimeters. So if that's the case, then what we found was volume. So that would be centimeters cubed. Because when you're finding volume, you're finding how many cubes would fit into this object.